you consider word of laptop, that is a one token according. Subword tokenization. Subword tokenization means dividing words into multiple tokens. Like if you we can say like a long word like we can say components. From the subword tokenization, components word can be divided into like two tokens. Character level tokenization. The character level tokenization means for each character there is a one token. For example, for the word of was, there is a three tokens. So the byte level tokenization. Byte level tokenization means tokens dividing into bytes, and represent as the tokens. So mostly these tokenization method use the BERT models. So the other one is sentence piece tokenization. These actually doing sentence by sentence, this tokenization method. So the other component is parameters. What is this parameter mean? Parameter means internal variable like weight and bias. So in this large language model, there is a bunch of neural networks. That is the architecture of these LLM models. For these neural networks, there is a variable called weight and bias. Weight mean basically the weight and bias mean basically the formula of these models. So when coming to the neural network, there is a loss function, cost function, and gradient unit for these things. These things reducing by these weight and bias. So the transformer architecture. Now let's dive into the transformer architecture. What is this transformer architecture mean? Basically, the LLMs are made from this transformer architecture. It has input impedance, positional encodings, attention mechanism, feed-forward neural network, and normalization and residential correlation. So the large language models are using this architecture to build their model. So basically, this transformer architecture can be divided into two parts: encoder and decoder. The encoder is the input embedding. The encoder has input embedding and multi-head attention, adnorms, feed-forward neural network, and again adnorm. So basically, what happens is the input embeddings. The first step of this transformer model is now you are giving an instruction. Like you are asking something from the model. So the model is first of all take this sentence and divide into tokens. So after that, after divided into tokens, there is a dictionary for all the words that model has a dictionary. From the dictionary, model is model find the words that you have given. So that is the input embedding doing actually. This step actually capture the semantic meaning of the tokens in a continuous vector space, allowing to the model understand the context of the relationship between the different tokens. So the positional encoding doing is unlike the traditional model like RNN and CNNs, these these models can't do multiple tasks simultaneously. So for because of that, the researchers has found this transform architecture. So the positional encoding comes they providing about the position is each token in the sentence. Like in our sentence, they are divided into tokens. So after that, from the positional encoding, they are giving position to your that tokens. This is directly input to the embeddings wherein in model to order the sequence of tokens, which is crucial to understand the content of language. So the other one is attention mechanism. The attention mechanism is the main part of this transform model. It allows models to focus on different parts in the input sequence when generating an output. So let's say you are writing a sentence and trying to understand it. You might focus on certain words depend on your depend on what you are going to write. So like this attention mechanism is doing the self-attention computes weights average of the input embeddings, where the weights represent the importance of the each token, the context of other tokens in the sequence. So the other one is feed-forward neural network. After processing through the multi-head attention mechanism, the output is fed into the position feed-forward neural network. This network consists of two linear transformation with ReLU and ReLU activation function. This is step further refine the representation of the input data, capturing complex relationship and patterns. So normalization and residential connections. So each sublayer, including the multi-head attention and feed-forward neural network, followed by layer the normalization. This step is stabilizes and accelerate the training process. Additionally, residential connections are used to add the input of a sublayer to the output. This help the mitigating the vanishing the gradient problem. So that is the basically the architecture of transformer model. So this architecture usually used for the large language model for the training. So let's move into the fine tuning. So what is the fine tuning mean? Fine tuning mean basically use these pre-trained models for train a specific task. For example, if you need to create a specialized chatbot like a medical chatbot, so you only need to provide that chatbot only that medical information, right? So if you take these pre-trained large language model, maybe this model has that information about that medical, but but this model will be giving the answers to other things also. So this is the for this we can use the fine tuning method. So fine tuning is a process of adjusting the parameters of pre-trained large language models to do a specific task or domain. So first one is the unstructured data. Before the train the LLM, to train LLM, there is a large amount of data, like terabyte of data. There is actually unstructured data because the data can't be structured and input into the LLMs, right? So these data actually unstructured data and feed into the training process in the LLM. Okay, so LLM will be learning by themselves to capture the patterns of this data. So after that, after pre-processing part, we have a pre-trained model, that means LLM model. Now after this we can fine-tune this model from custom data. If we have custom data set, we can feed this into that pre-trained model, and straight away a model will be answering according to that custom data. This custom data should be actually supervised data, because we are giving some instruction to train this model. So after that we have fine-tune model. So that is the actually like fine-tuning. So after that we have fine-tuning methods. So full fine-tuning. What is this full fine-tuning meaning is, now in the large language model there are a lot of parameters and parameters, right? So this can be different model to model. There can be 1 billion parameters, 7 billion parameter, etc. So this can be very large according to the model. So full fine tuning means taking these all the parameters and fed into our fine tuned model. So but there is a issue with this. So when we are training with that lot of parameters that have fed into our LLM model, this can be tend to overfit. That's mean there are a lot of parameters, but our custom data is not large for this fine tuning. So because of that, this can be overfitting. Also another problem is cost. So these parameters are a lot of parameters and a lot of data. So because of that, we need high computational. We need high computers to run these models. So so our local computers are not powerful like this. Because of that, the full fine-tuning method is not good for this fine-tune method. So to address this, we have PEFT method, parameter efficient fine-tuning. This is like a this is fine-tuning only a small number of parameters. This can be significantly decreasing the computational and storage cost, while yielding performance comparable to a full fine-tuning model. That's mean so we have like 7 billion, 8 billion parameters in our LLM models. So basically most of these from this PEFT method, what is doing is most of the parameters are freezing, and by freezing, then taking into the our fine-tuned model. So for this PEFT method, we have like LoRa. So the LoRa is a way of train large language models efficiently by increasing the trainable matrices and parameters. So LoRa is doing is freezing the existing parameters and adding a small neural networks into it and fine tuning from that. And also we have another one also, prefix tuning. This technique is depends on learnable tokens, two input circles. These preferences are trained while the main model parameters are kept constant. That means all the parameters are being temporarily disabled, and there is a new parameters and new networks fed into this fine tune method. So tools for fine tuning using LLM. So to fine tune these LLMs, we can't do this in our local machines. So we can, but we need high computational power. But for that, like Hugging Face, like Google, like Kaggle, those companies have given us to some tools for fine tuning these models. Hugging Face. From Hugging Face, we can take actually models, transformer models, LLM models, a lot of models, even data set. Also, we can get from the Hugging Face. And the Google Colab is basically a Jupyter Notebook inference that made by the Google. From this Google Colab version, from the free version, you can the Google is given 14 GB GPU and 12 GB RAM. So from that you can fine tune like a llama model. So this is more than enough to like train the llama. So and the Kaggle also given us to the data sets and Jupyter Notebook inference to train the model. So now let's move into the fine tuning, electrical fine tuning. So I have already fine tuned model, actually the bird model. So I will be explaining the codes. So the first one is we need to install our parameters, our libraries. So then we need to import that. So we need transformer library. This transformer library is based from actually Hugging Face. So from that we can take the transformer architecture, and PEFT method mean that I have mentioned earlier about that parameter efficient fine tuning. So we are also taking that. So now from these transformers we are importing the bird classification. Today in here I'm going to train the classification model, actually sentiment analysis. So we need training arguments and train. also the evaluation method. So I have using this IMDb dataset. So I have directly import the dataset actually, and then we need, after the importing the dataset, we need to pre-process the this dataset. We need to actually import a tokenizer. So we are using the, since we are using BERT model, we need to use this token based on this BERT model. So to model, this can be different, the tokenization. So we need to specify the tokenization, and after that, from, since this IMDb dataset is very large, I have made that into a smaller dataset to fine tune. So this is it, and after that we have I have mentioned the LoRa configuration. So what is this LoRa configuration mean? That I have previously mentioned that we have taken some special parameters to train. So this is only training like from the full model, it's only getting like 15% of parameters. So after that I have imported the model. So I have imported the model with LoRa configuration, and I have then I have imported the model with LoRa configuration. So then the summary of the model. So here you can see in the BERT model, the BERT classification model, this has like lot of parameters, right? But we are taking only 38,402. So there are noticeable parameter gaps in here. So after that I have put the training arguments, 30 epochs. Epoch mean basically the model is going one iteration, like forward and backward propagation at one time. So that is the one epoch. So epoch, so I have mentioned 30 epochs, that my model will be doing continuously 30 times that. So then I have import the trainer. So here is the 30 epochs. So this no log mean there is a no loss in these epochs. So up to 17 epochs there is a no loss. After that there is a loss. We can see the loss, and so I have saved the model and test by this sentence that this is actually sentiment analysis. So I have input a text and get the result, that is whether this sentence is positive one or negative. So guys, that's all about it. So I think you gain some intuition about LLM models.